Video 10 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is the molecular electronic Hamiltonian. Now we want to collect all the terms which we have derived in the last two lectures for the one electron case and generalize the expressions for the many electron case. In a minimal coupling approximation, both non-relativistically and relativistically, the vector potential of the electromagnetic fields enter the mechanical or kinematical momentum of the electron pi. As a consequence, the mechanical momentum, the one which goes into the kinetic energy expression, and the canonical or generalized momentum of the electron are then no longer the same, because the mechanical momentum is the canonical momentum plus the elementary charge times the vector potential. Now, right now, we will stay within the Born-Oppenheimer approximation, which means that we are ignoring the kinetic energy operators for the nuclei. But in principle, the kinetic energy for the nuclei would also be rewritten in this form, because the mechanical momentum of the nuclei also has to be modified by including the vector potentials. But since we not include the kinetic energy at all, we are not going to have this term. However, we will include the terms coming from the interaction of the nuclear charges with the scalar potential. So we will include terms where not only we have the term with the scalar potential and the charge of the electrons, but also the corresponding terms with the scalar potential and all the charges of the nuclei. In addition, we will include the Siemens term of the Pauli Hamiltonian, which we just have derived in the last lecture, which is the interaction of the spin of the electrons with the curl of the vector potential. Now, in principle, there is of course a corresponding term also for the spin of the nuclei, but again, this we will not include in our Hamiltonian. Including all those, we can write the Hamiltonian, the molecular electronic Hamiltonian, in the presence of an electromagnetic field and in the Born-Oppenheimer approximation in this way, where I have grouped all the different terms here and I label them with an order symbol here to 0th order, 1st order, and 2nd order, depending on whether the vector or scalar potential are included in those operators and whether the operators are linear in the scalar vector potential or quadratic in the scalar vector potential. Which means that the first three terms here, those three, they are the 0th order Hamiltonian, and they are actually the terms which we had already in chapter 2.2 on the Born-Oppenheimer approximation. Whereas these two terms, they form together the first order correction to the Hamiltonian, and finally this term here is going to be the second order correction to the Hamiltonian. In this part I have to written up. So small operators H and G, and H, first order H here and the second order H, those are operators related to the electrons. So here in H0 we have the kinetic energy operator for the electrons and the interaction, the attractive Coulomb interaction of the electrons with the nuclei. G is the electron repulsion operator, and all the capital H operators are nuclear operators, meaning operators which only depend on the position of nuclei. And here we have there also in the Born-Oppenheimer approximate the constant term for the Coulomb repulsion of the nuclei. Corresponding the first order Hamiltonian then includes electronic terms, and here we have then the scalar product of the vector potential and the canonical or generalized momentum of the electrons, where again, in order to arrive only at this term, we have used the Coulomb gauge as shown in 2 lectures before. Then we have the electronic Siemens term here, and finally we have the electronic charges multiplied with the scalar potential. And we have a corresponding term for the nuclei, which is again the nuclear charges here times the scalar potential. And finally, the second order term, we have only an electronic term, which is essentially the square of the vector potential. As I said before, because we neglect the kinetic energy of the nuclei, we don't get terms corresponding to this one and that one for the nuclei in our Hamiltonian. Now in the following chapters, we will then consider different electromagnetic fields and therefore derive expressions for how precisely the vector potential and the scalar potential look like. And then we typically will end up writing the Hamiltonians, the perturbation Hamiltonians, meaning the first order and the second order perturbation Hamiltonian, in a form like given here, where we will separate parts of the operators which are essentially just the components of the external electric fields or magnetic moments, and parts of the operators which only depend on the position or canonical momentum or spin of the electrons. And those operators O I will then call interaction or perturbation operators, whereas the total H I will call the perturbation Hamiltonian operators. You might wonder what this notation alpha ... or alpha beta ... is meaning. Well, the reason for that is that we will have not only external fields with 3 components, but we will also look at field gradients, where we'll have 9 components. And in order to cover these different cases in the same notation, I invented this alpha ... So F alpha ... can cover components of a vector field, where there would be 3 components, but it can also cover components of a second rank tensor field, where we'll have 9 components, and correspondingly the interaction or the perturbation operators O alpha ... could be the 3 components of a vector operator, but it could also be the 9 components of a second rank tensor operator, and correspondingly here with 2 components there it could be a second rank tensor, or it could be a third rank tensor, and so forth. And we are now in the many electron case, and therefore we have capital operators A, and they are of course then a sum over the corresponding operators just for the individual electrons. So our total interaction perturbation operators are the sum of interaction or perturbation operators for each individual electron, which like usually I notate with small letters for the one electron case, in contrast to the capital letters for the many electron case.